Hey guys, I am back here, and right now I would like to talk about something called hybridization. Hybridization basically describes something that can happen with atomic orbitals in order to provide a better model for explaining how they make the types of bonds that they do. And that's something that's actually not very well explained by some of the other orbital theories that you may have learned about originally in Gen Chem. Let me give you a for example here. All right, I want to take a look at a molecule called methane. Methane is CH4, and it looks like that. Okay. All right, so you can see here, we're going to look at the carbon. The carbon does what we would expect carbon to do based on the guidelines that I've told you in the past, right? Carbon likes to make four bonds and have no unshared pairs of electrons, right? Let's see why that is. You can actually link that and see directly how hybridization explains why this is the case. All right? Something that you should know, first of all, about bonding electrons. There's two requirements for an electron to be able to form a bond with something else. All right? Number one, has to be valence. Only electrons in the outer shell are capable of overlapping with other atoms and their electrons to form bonds. Number two, these must be unpaired. If they're already in a pair, they're not going to form a bond. All right? And you can think back to the when you talked about orbital theory, right? You remember individual orbitals can hold up to 2 electrons, right? So you could go through the filling process, and in certain cases you might have an orbital that has only 1 electron. Other cases you might have one that's completely full with 2. Once it's completely full with 2, it is set. It is happy. It doesn't want to do anything else. So those are not going to bond. The only ones that will bond are the unpaired ones. All right. So if we kind of do some deductive reasoning here, we can kind of deduce that, in this carbon right here, this one in methane, we can say that this carbon should have 4 unpaired valence electrons because it's making 4 bonds. All right. Well, let's try to map out these valence electrons in atomic orbitals to see whether this is the case or not. All right. Remember, we're only dealing with outer shell, outer energy level. So for carbon, that's going to be energy level 2. And if you remember, energy level 2 is going to have 1 s orbital and 3 p orbitals. All right. Let's fill up these orbitals with the 4 valence electrons that carbon has. All right. If you remember your rules from Gen Chem, right, you remember that you completely fill orbitals and levels of lower energy before moving up to higher energy, right? The s orbital is going to have lower energy than the p orbitals, so the first 2 are going to go in there. All right. So that means we have 2 more electrons to put into the p orbitals. Now, since we have multiple orbitals of equivalent energy, we basically go one at a time, right? So we go 1, 2, and that's it, right? That's all we got. We just have 4. All right. Now look at this. We know carbon has 4 bonds. We know it needs to have 4 unpaired valence electrons. But if you look here, I only see 2. The other 2 are in a pair already, right? They're happy. They're not going to bond. So according to this model, this carbon should only make 2 bonds, right? So you can see there's a deficiency there. There's a disconnect. This model does not accurately describe what happens with that carbon atom. All right? And that's where hybridization comes in. Atoms, when they get ready to covalently bond, they can actually take their orbitals and they can sort of transform them into other forms, all right, through hybridization. All right, I'm going to draw this again. All right, so that's what we have. What we do in hybridization is basically we take some combination of this s orbital and these p orbitals, and we sort of mash them together. They combine, or they hybridize, in fact. All right. So let's say all of these hybridize. These all smush together. All right. There's a rule, and I'm going to try to squeeze it in down here. When you hybridize, orbitals in equals orbitals out. That means that if you start off hybridizing 4 orbitals, like we do here with 1 s orbital and 3 p orbitals, that's a total of 4. We must spit out 4 orbitals as well. All right. We are going to do that, and it just so happens that these 4 orbitals are of equivalent energy because they're all the same type. I'm running out of room here, so pardon me if it's a little squished. These are all what we call sp3 orbitals. And you can probably figure out why they're called sp3. It's because they're made of a singular s orbital and 3 p orbitals. They have all equivalent energies, right? So now, if you try to map out the 4 valence electrons, they go 1, 2, 3, 4, and voila, we've got 4 unpaired valence electrons. So this, right here, is a much more accurate model of what's going on with the carbon whenever it makes covalent bonds. Pretty cool. And this applies to other atoms that we commonly use as well. Let me erase and I'll show you. Let's take a look at the nitrogen in NH3. Okay. Nitrogen, just like we've seen before, its preference is to make 3 bonds and have 1 unshared pair. I'm about to show you why. Nitrogen, just like the carbon in the previous example, has sp3 orbitals that can be used for bonding. Okay, so nitrogen's in group 5, so that means it's going to have 5 valence electrons, so let's fill them up. 1, 2, 3, 4, 5. Alright, and if you look at this, we have 1 orbital that's completely full. It's got a pair, those electrons are happy, those are not going to be involved in bonding. That corresponds to the unshared pair that you see sitting on top of nitrogen right there. These 3 orbitals each have a singular electron. That means each of them can be involved in a bond. And that's what you see with the 3 single bonds to hydrogen, right? So you can also explain the preferred bonding pattern of nitrogen in this case. Let's take a look at oxygen. It works for oxygen too. All right, let's take our old good friend water, H2O. And as you know from the rules, oxygen likes to make 2 bonds and have 2 unshared pairs. All right, we're going to do the same thing. All right, now oxygen's in group 6 of the periodic chart, so it's going to have 6 valence electrons. So it's going to go 1, 2, 3, 4, 5, 6. All right. 2 completely filled orbitals means 2 unshared pairs. And we have 2 hybrid orbitals with unpaired electrons that can be involved in bonding. Those that are going to correspond to the single bonds we see to hydrogen. Oh my goodness, I just realized I misspelled hybridization. How embarrassing. I can't believe nobody corrected me on that. With your mind powers. Apologies for that. I'm ashamed. Alright. Alright, so those are some good examples of how you can form sp3 orbitals in order to explain some of the common bonding patterns. Now, sp3 orbitals aren't the only ones that we can make, though. Let's take a look at this example. We're going to toss a double bond in there. And we could look at either one of the carbons. I'm just going to, pick that one, just for funsies. Okay. Now, this one's a little bit different because here we introduce a different type of bond. All right. And at this point, hopefully you guys remember from Gen Chem the difference between sigma bonds, or excuse me, sigma electrons and pi electrons. If you don't, I'm going to explain it to you real quick, but if you need further explanation, please go back and review this. All right. Remember, all single bonds are made using what we call sigma electrons. Okay? Within double bonds, one of the bonds is made from a sigma pair of electrons, one of them is made from a pi. All right? So in this case, if I'm circling the double bond there, one of those pairs is sigma, one is pi. If you have a triple bond, which we'll look at in a minute, we actually have a triple bond. They are made out of one sigma and two pi's. Okay? That's going to be important to know because I want to lay out a couple more guidelines for you. Sigma electrons, they're always found in hybrid orbitals. And we saw that, and we saw that with the last few examples that we did, right? We made a bunch of sigma bonds. Those sigma bonds were made from hybrid orbitals that contained unpaired electrons, all right? However, pi bonds are going to be a little bit different. Pi electrons are always found in p orbitals. Just strictly p orbitals, not as part of a hybrid. All right, this is going to be our first example where we see something like that. And while I'm talking about it, might as well mention unshared pairs. Unshared pairs, they aren't picky. They can go in either one, just depending on what's available at the time. All right. Remember these guidelines, though. I want to show you how the hybridization works in this particular example. All right, so let's take a look. I want to draw this little dilly again. Right, we have our 3p orbitals and our s orbital. Now, we saw how they can all combine together to make sp3s. They don't necessarily all have to combine. Sometimes the s orbital will combine with only two of the p orbitals. All right. So if we go by the orbitals in, orbitals out model, we combine three orbitals here, one s and two p's, and we should get three hybrid orbitals. And those are going to be not sp3, but they're going to be sp2. Okay? Now you notice we have something left over. We have a p orbital left over. For all intents and purposes, the energy of this p orbital is going to be about the same as the hybrid orbitals in this case. So we can draw it on an equivalent line. That'll be important when we map our electrons out in just a second. All right? All right, so let's take a look at this carbon again. Right? We said that carbon, just like any other carbon, is going to have 4 valence electrons. Right? So if we try to map those 4 valence electrons, boom, 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 here you see an interesting situation. 3 of those unpaired electrons are in hybrid orbitals. That means that we are limited to the number of sigma bonds we can make. Remember, sigmas have to be in hybrid orbitals, so if we only have 3 unpaired electrons in hybrid orbitals, that means we can only make 3 sigma bonds. All right? And if you look at this carbon again, well, it's got a single bond to hydrogen, that's 1. It's got a single bond to another hydrogen, that's 2. And it's got a double bond to carbon, right? Remember, 1/2 of a double bond is sigma. So that explains all your sigmas. The only thing we haven't explained yet is where do we get the pi bond? That's going to be from this guy right over here. That electron's in a p orbital, so that one can bond with another of the same type to form a pi bond. All right? So this model explains why, in a case like this where we have a double bond, we can have the formation of pi bonds. Excuse me. Let me show you another example. All right, now in this case, we could look at either the carbon or the oxygen. I encourage you to do both on your own, but for right now, I'm going to go over the oxygen with you. All right? This is going to behave just like the last one. This one's going to hybridize as to form 3 sp2 orbitals. And you're going to have a p orbital left over, right? So according to the periodic table, oxygen has 6 valence electrons, so let's fill them in. 1, 2, 3, 4, 5, 6. All right. These guys are going to be unshared pairs, so we have 2 of those, and as we can see in oxygen we have 2 unshared pairs. We have only 1 unpaired electron that's in a hybrid orbital. So that means oxygen in this case can only make 1 sigma bond. All right? And the 1 sigma bond that oxygen has here is 1/2 of your double bond. We also have 1 electron left over in a p orbital. That is going to be used to form the pi bond portion of your double bond. All right? So that is how sp2 orbitals work. There's one other type, and you probably can guess what it's called. It's called an sp orbital. All right? Let's take a look at one like this. All right? And we can look at either carbon here. They're basically the same. We'll just look at this one. All right? If you look at this carbon, ask yourself, in this structure, how many sigma bonds is it making? How many pi bonds is it making? Give you a second here. See if you can predict what you're supposed to be looking for. All right. In the meantime, I'm going to show you how the orbitals hybridize in this particular case. All right. Like I've said, we're going to make sp orbitals. So that means you have 1 s orbital combining with 1 of the p orbitals. And that'll form 2 sp orbitals, and you'll have 2 p orbitals left over of about equivalent energy. Okay? So again, you look to see how many valence electrons you're working with. Carbon's going to have 4, so let's put them in their places. All right? So hopefully when you looked at the structure, you could tell that carbon in this case was making 2 sigma bonds, right? 1 to the H, and then basically 1/3 of the triple bond is a sigma. We have 2 electrons available for bonding in hybrid orbitals, so that makes sense, right? We also have 2 pi bonds, so that means we need 2 unpaired electrons in p orbitals, and that's what we got over here. So, voila, that works. When you guys are doing this, again, hybridization is one of those things that some people have a little bit of a hard time with initially. So if you're having any questions for me or any struggles as you're doing this, please let me know. All right. So you may ask me, okay, Dr. McFarland, I know that you, in all of your infinite wisdom and genius, can tell what's going to go on here, but how do I, a humble beginning organic chemistry student, know whether something's going to hybridize to sp3, sp2, or sp? You are in luck, because we have guidelines, we have shortcuts, and that really sort of cuts to the chase of what I want you to be able to do with hybridization. The biggest thing I want you to be able to do is look at a structure and be able to tell just right off the top of your head, that was a snap by the way, what its hybridization is. Is it an sp3 hybridized atom, sp2, or sp? Okay. What we do is, is we count the number of what we call groups on an atom. Okay? A group, just to tell you what a group is, it's not a Z, it should be an equal sign. Either another bonded atom or an unshared electron pair. Okay? So for example, in methane, if we're looking at the carbon, this carbon has 4 groups on it, right? It's got 4 bonded atoms, no unshared pairs. 4 plus 0 is 4. Water, if we're looking at the oxygen has 2 unshared pairs, has two bonded atoms. 2 plus 2 is 4 groups, right? So figure out how many groups are on an atom. That's how you get started. It's very simple. If you have 4 groups on an atom, its hybridization is going to be sp3. If you have 3 groups, it's sp2. 2 groups, it's sp. That's it. Very, very simple, very straightforward, but very accurate as well. All right. So if you can look at an atom in a molecule, count the number of groups, then you're golden. You can tell immediately what type of hybridization it's going to be. That's going to be super, super important later on because as we're going to see as we go along, there are certain reactions that only work with certain hybridization states, right? So a reaction that we might be able to do with an atom in sp2 hybridization might not work with an atom in sp3 hybridization. So being able to recognize that is going to be important. All right. I also want to mention, in addition to hybridization, a couple of factors that you guys have talked about before. I'm sure ad nauseum in Gen Chem and also high school if you had it there. That is the geometry around an atom and bond angle. All right. You also need to recognize these from structures. Now, the good news is we don't care about all the geometries, right? For example, I don't give a crap about octahedral or trigonal bipyramidal. That doesn't involve the stuff I care about, right? We care about tetrahedral, trigonal planar, trigonal pyramidal, linear, and bent. All right? There's really no better way to tell you this than, again, sort of make a little chart. This is going to be a case where, again, I use the M word. Just memorizing this will give you a good basis. All right. So I have limited amount of room on here, given that I have a big fat stylus here and a small tablet. So I'm going to make a couple of abbreviations. All right. I'm going to use G for groups, where I'm going to get a little bit more descriptive about the groups. I want to use H for hybridization, Geo for geometry, and A for angle. And basically what I'm doing, I'm sort of expanding on that chart I just made a couple of minutes ago, describing what you see with the groups and the hybridization. I'm going to extend that to geometries. All right, and we can also get a little bit more specific with our groups. All right, so let's start. Let's say your groups, let's say you have 4 groups, but specifically they're 4 bonded atoms. I can already tell I'm going to have to erase some of this, but that's okay. All right, so let's say you have 4 bonded atoms. All right, a good example of this is methane, like I just showed you before with CH4. Of course, we said this hybridization would be sp3. That's going to have a type of geometry that we call tetrahedral. And it means the molecule basically extends out into 3 dimensions. Okay? We're not going to focus on 3-dimensional stuff too much until we get to a future chapter, but there is a basic review in here of how to draw these, so I would recommend taking a look at it in Chapter 1. It'll show you how a tetrahedral geometry is represented whenever you draw a chemical structure. And in a tetrahedral arrangement, we always have a bond angle of 109.5. Okay? All right. Now, let's say we have something where we have 3, why don't you say, yeah, never mind, I'm talking to myself. 3 bonded atoms, 1 unshared electron pair. All right. This is like the nitrogen in NH3. Right? We saw it made 3 bonds to hydrogen and then had 1 unshared pair. All right? It's still got 4 groups, so it's still got sp3 hybridization. Right? However, it is going to have a little bit of a different geometry, all right, and a different bond angle. These are slightly adjusted into something called a trigonal pyramidal arrangement. And their bond angle is close to 109.5, but it's deviated a little bit. Whoops, there's not a Z there, I'm pretty sure. It's going to be 107 degrees. Okay. Now, we've also seen that we can have 2 bonded atoms. And 2 unshared pairs. This is like the oxygen we saw in water, right? Now, again, it's got 4 groups, so it's still sp3, but has a different geometry. I'm sure you guys are probably well versed with the geometry of water now. Altogether, water is a blank molecule. It is bent. Bent, just like trigonal pyramidal, is sort of another derivative of a tetrahedral arrangement. Very similar, just a little bit off. It's got a bond angle of 105 degrees. Okay, so you can see, even within sp3 hybridized atoms, you can have a little bit of variation in geometry and bond angle. All right, bear with me here. I'm going to erase some of this because I have a couple more to put in. Talk amongst yourselves while I'm doing this. Have a conversation with your neighbor or the voices in your head. Either's fine. Okie dokie. Alright. Now, we've also seen that we can have 3 groups. And in this case, it doesn't matter. We don't have any delineation between, 3 bonded atoms or 1 bonded atom and 2 unshared pairs or anything like that. We can take these all together. All right, 3 groups, and we saw that the hybridization is going to be sp2. All right, if you have an sp2 hybridized atom, its geometry is always going to be trigonal planar. And this is a little bit different from the other 3 that we just went over, which are all 3-dimensional arrangements. This one's actually 2-dimensional. You can tell from the name, planar, right? Flat as a sheet of paper. And that'll be important because we will see several reactions later on that work only with planar arrangements. All right, bond angle in a trigonal planar geometry is 120 degrees. All right, lastly, we see we have 2 groups. Right, again, we don't have to do for different combinations here. This applies to all situations where you have 2 groups. We know those are sp hybridized. These have linear geometries, right? Just in a straight line, bond angle of 180 degrees. All right. Be sure to go over all this and also make out the charts that I have outlined. Study those, commit those to memory, and also get some practice on the problems to help applying it, to help you apply it. Because like I said, really my goal here is to get you to be able to look at a structure, look at an atom, tell me, okay, what's its hybridization, what's its geometry, what's its bond angle. All right, that is all for right now. So until next time, have a good day.